Hello, this is Zach back with another video for Students Teach Orgo. This video is going to continue our conversation about enol and enolate chemistry by discussing the aldol condensation. I'm going to break up this video into three parts. We'll start off by talking about the mechanism. And we'll start off by talking about the mechanism in base, because that's typically how you'll see it done. The aldol condensation starts off with the aldol addition reaction and then is followed by a loss of water to make the condensation product. It's a reaction that can occur between two aldehydes. It can also occur with ketones or between a ketone and an aldehyde, or later, as we'll discuss, can also happen with esters, but when it happens with esters, it gets its own name. It's called the Claisen condensation. Anyways, back to this part. The first step of the aldol condensation is this aldol addition reaction where an aldehyde or a ketone that has an alpha hydrogen can go and transform into this aldol. And we call it an aldol because of the aldehyde and the alcohol, and so we kind of just put those two together to call it the aldol. And so let's take a look at how this mechanism works. To start off, we have hydroxide as our base, and it's going to pull the hydrogen off of the alpha carbon. And remember, this hydrogen is slightly more acidic because we have these resonance structures here. It's a stabilized anion. This is what I normally think of when I think of an enolate, but this resonance structure is important too because it shows that the carbon has a partial negative charge on it, and so it's going to be nucleophilic. So the first part of the aldol condensation is pulling off your most acidic hydrogen, the hydrogen on the alpha carbon, to make an enolate. And I like how this slide points out too that the enolate is not favored in this reaction. This big arrow to the left here is showing that the aldehyde is actually much more stable than the enolate here, and that's because the enolate is much more basic than sodium or hydroxide is, and you can see that with the pKa's. However, because in the aldol condensation this enolate is going to get used up, and there's always a little bit of enolate that's in equilibrium with the aldehyde, that this reaction will go forward. So in that last slide, we made our enolate, which is right here now, and they're showing how that carbon, right, that has the negative charge, can now attack the carbonyl carbon of another molecule of the same aldehyde. Remember that carbonyls, the carbon of the carbonyl has a partial positive charge because oxygen is electronegative, and so by attacking that carbonyl carbon, we're going to get this product right here, and then we can just have this O- grab a proton from water to create the aldol. Now, if we take this a step further, actually here, let's look at this first. So that is the aldol product that we just made, and we made that by putting in an aldehyde in a solution with base, an aqueous solution with base. If we add some heat, we're going to push this aldol to the condensation product, where you can see we're losing water, right? We're losing that hydrogen and that OH as water to create a double bond. And let's investigate the mechanism for that part. So we heat up our beaker, and now hydroxide is going to pull another hydrogen from this alpha position of the aldehyde to remake an enolate. So the negative charge here, you could also have drawn it where those electrons go there and push the electrons up onto that oxygen. Same thing, right? Just a different resonance structure. But now that we have that enolate, the enolate is going to push out OH. Now, OH is usually a really bad leaving group, but this E1CB mechanism helps kick out OH. Normally, OH just doesn't leave by itself, but that will give us that double bond that we see in this condensation product and have us lose water. So I've redrawn out this mechanism using Oscar just because I like the way Oscar looks, and I've done this from start to finish here so you can see it all at once. So we start off by having our base attack the alpha hydrogen, making our enolate. I usually draw my enolate like this. Then you can see we're taking the negative charge, kicking it back down, and having this double bond attack the carbonyl carbon. Some students ask me, they ask me, oh, well, if there's a double bond here, how do we know which of these two carbons is going to be attached to this carbon? And the answer is, if we're bringing electrons down here to make a double bond, this carbon's already going to have 4 bonds. So it has to be this carbon right here that's going to be making the new bond between here and here. So you can see then we have our aldol, but it's just got that O with a negative charge. Now, if that was it, right, we could have water and we could protonate it by having that go there, and we would get our aldol product. However, if we heat it up, then we're going to just do a little proton transfer here where we put an OH down here, but we also make an enolate at the same time. And then this is that E1 elimination, E1CB, where now this is going to push down its electrons, moving this double bond down, and when this double bond moves down, that kicks out OH and gives us our condensation product. The aldol condensation can also occur in acid, and I'm going to go through this one a little bit faster because it's super similar to the one seen in base with just a few extra steps because we have to protonate some carbonyls. So in acid, we're going to start off by having the carbonyl attack hydronium and grab a proton. This is a very common first step if you've seen a lot of Orgo-2 reactions. By protonating that carbonyl, we make that carbonyl carbon even more electrophilic. So now what's going to happen is water can pull that alpha hydrogen, and we can make our enol. The enol can now attack another molecule of the aldehyde, and right here, right, when this double bond attacks the carbonyl carbon, I could have put that charge up on the oxygen, but we then have a negative charge, and generally for mechanisms when you're in acid, it's not good to have a negative charge. So instead, we're just going to have that double bond go out and grab a hydrogen. And so that will take us directly to here, where you can see these carbons are these carbons on top, and then this molecule is now stuck to the bottom, right there like that. Now I'm just going to take that molecule and draw it again over here. So this was the aldol addition part, and now we're going to do the condensation part. You can see I've got heat underneath the arrow. We are going to protonate the carbonyl again, and now this is just a proton rearrangement step where this OH is going to grab this proton to remake our enol, and at the same time that's going to make water. So we have an enol, we have water. Water is a great leaving group. And by using the electrons between this oxygen and hydrogen, we can remake the carbonyl, move that double bond down, and kick out water, which makes the same dehydration product that we saw in the base mechanism, just by a different set of curved arrows and in different conditions. So here is our first practice question. It's not a super creative question, I will admit, but watching me go through the mechanism probably isn't going to be enough to cement it in your brains, so I would highly recommend trying to get a piece of paper or your iPad or whatever and just go through those two mechanisms that I just showed you, the one in base and the one in acid. If you want to check your work, just go back to the earlier parts of this video here, but I think it's a really good idea to practice these mechanisms by drawing them out yourself. And so then for the second practice question here, this one will be slightly less work. We've got 4 different molecules here, and I'm asking you what is the product of the aldol addition reaction? And I'm asking not for the condensation product, right? So pause the video here, try to figure out which one of these would be the aldol addition product. I'm going to go forward. The correct answer would be C. And so if you go through the mechanism, you would arrive at C. But I feel like this is probably a good opportunity for me to show you a little bit of a shortcut, right? So you can see this right here is the same as the aldehyde that you started with, right? So these carbons, are these carbons in the product. And what you can see is that the alpha carbon is now attached to another molecule of the aldehyde, but now that aldehyde has kind of been reduced to an alcohol, right? So you can think about it as this is one molecule of the aldehyde, this is the other molecule of the aldehyde, and the part that's the aldehyde still, at its alpha carbon, is attached directly to the same molecule. So that's how you can kind of split it apart and see where it came from the reactants. All right, next we're going to look at the mixed aldol reaction. I've got a bit of a rhetorical true-false question here, because I'm sure you guys can imagine that this will not be the only product. It's not going to be that simple. You can see in this case we've got two molecules that are both aldehydes, but they're slightly different, right? This one's got a methyl group, this one's got that ethyl group there in blue. And unfortunately, we cannot have a nice aldol reaction to make just this product. We're actually going to end up getting 4 products, and that's if you ignore the stereochem of that OH. When you go to the condensation product, right, so if we added heat to these molecules down here, we would make a double bond, and that double bond could be cis or trans, so that increases the possible number of condensation products to 8. So this is a very messy reaction, gives you a ton of different products. And so to show how that happens, right, the first step in the mechanism that I was just describing is making the enolate. And so if we put both of these molecules in a test tube and put in some sodium hydroxide, we could make an enolate either from molecule A here with the methyl or molecule B with the ethyl. Now in the next step, when we go to attack the carbonyl carbon with the enolate, there's these 4 different possibilities, right? We could have enolate A attack a molecule of itself or a molecule of the other aldehyde, or we could have enolate B attack itself or a molecule of the other aldehyde. And that's going to lead to these 4 crossed products, right? And it's important to notice here that A and B and A are slightly different here. Notice that over here it's the methyl group that's kind of between these 2 oxygens, but over here it's the ethyl group that is between the 2 oxygens. So 4 different products. Now there is a way that we can kind of control and sometimes get less products from this crossed aldol reaction, and that is if we specifically choose an aldehyde that does not have an alpha hydrogen. So this aldehyde right here doesn't have a hydrogen, which means it's non-enolizable. We can't make an enolate from this hydrogen, or from this aldehyde, sorry. I drew another example of a common non-enolizable aldehyde that you might find. Because this carbon is quaternary, it's not attached to any hydrogens, so we can't make an enolate out of this. Now there's special laboratory equipment that you can use to either slowly add in the enolizable aldehyde, or maybe you can just have that enolizable aldehyde at a really low concentration, but you can pretty much get just this cross product as a major product if one of your aldehydes is non-enolizable. So here is our third practice question. This is a doozy, it's a big one, there's a lot of drawing here, I apologize, but here is a crossed aldol reaction, and I'm asking you to draw the 4 aldol products and the 8 condensation products. So if you guys can do this, then you can be very sure of yourselves that you've got this part mastered. So I would pause the video here, spend some time, draw this out. I'm gonna move forward. Alright, so these were the 2 aldehydes that we started with, right? The one that has 2 carbons and then the one with the isopropyl group. To start off here, these would be the 4 different aldol products. And if you're confused how I got these 4 products from these 2 aldehydes, I would probably go back and go through the mechanism, make an enolate from this aldehyde, have it attack itself, another molecule of itself, or a molecule of this aldehyde, and then do the same thing for this one. So you can see like this one up top is the self product from this. This one at the bottom is the self product from this. Anyways, I think you guys got that. If we heat it up, that's going to push us to the condensation product. And these would be the 8 different condensation products. If you notice here, these are both stereoisomers, these are both stereoisomers, and so on. The only difference here is that one is in the E configuration and one is in the Z configuration. So just recognize that when you lose water and you make that double bond, you're going to end up getting a mixture of E and Z as well, which is why these crossed aldols are kind of a mess. Practice question number 4, choose the structure that would not be one of the possible aldol products from this crossed aldol reaction. Pause the video. Alright, the answer is going to be E, and I think a good way to explain that might be process of elimination here, because if this is not one of the possible products, that means we should be able to get A, B, C, and D from this mixed aldol. So to start off here, if we look at A, we can see that that is one came from this aldehyde, and this also came from that same aldehyde, and we made that bond in the reaction. If we look over here, we can see that this part again came from here, and that this came from over here. So both A and B both came from the same enolate. When we turned this into an enolate, we got something that looked like this. And then that enolate, the electrons came down, this double bond attacked, and in A, it attacked that carbonyl carbon, and in B, it attacked that carbonyl carbon. And I hope that you guys could see how that these A and B would come from this enolate. If we look at C and D both come from the other enolate. If we made an enolate from this molecule, we would have the benzene ring, and the enolate would then look something like this, where when the electrons and the oxygen come down and the double bond attacks, you can see that this right here is this aldehyde, and we made this bond to that aldehyde, and then over here, this was originally the enolate, and then this enolate attacked to make this new bond right here. In E, this doesn't work. There's no way that you could do an aldol reaction and get E. This hydroxide, this OH, is just in the wrong spot for that to have happened, and you can see that this aldehyde is now a ketone, and yeah, E doesn't work. To finish up this video now, we're going to talk about the retro Aldol condensation. And as the name implied, it's just going to be the Aldol condensation, but in reverse. So on this slide, I just copy and pasted the forwards Aldol condensation reaction from earlier in this video. And I just want to have that here so that way we can figure out this mechanism and how it works in reverse. So you can see that when we were going forward, our very last step was kicking out OH. And so it makes sense that in the retro Aldol condensation, our first step is going to be adding OH by having hydroxide attack at this position. This is called conjugate addition. We're actually going to talk about this more in the Robinson annulation video. But by attacking at this remote position, we can push over the double bond and put the electrons up onto that oxygen. You can see that next, going backwards in the forward one, kind of doesn't make sense, but I hope you guys know what I mean. We had this proton transfer here where we made an enolate by having this O- grab a hydrogen. So going backwards, we're going to do the exact opposite. Instead of making an enolate, we're going to take apart the enolate by having the enolate attack this hydrogen, and instead of having a hydrogen go to that oxygen, we're going to have the hydrogen leave from this oxygen to give us that O- here and the aldehyde up top. Now this is a tricky set of arrows because normally you don't see electrons move like this, but the next step going backwards, right, is the separation step where the two molecules attack each other. So it makes sense that now we're going to create two separate molecules. And you can see this O- is going to make a double bond here. There is a hydrogen right here, so something's got to get kicked out. And in this case, the best leaving group is actually this whole thing right here. And so we can then make an enolate, and then the first step in the aldol condensation is making an enolate, so it makes sense that the last step in the retro aldol is taking apart that enolate by having the enolate attack water, and then you would get 2 moles of this aldehyde right here. Alright, last practice question for this video. Draw a curved arrow mechanism of the following isomerization reaction. Determine the location of the radiolabeled carbon in the product. So this question has 2 parts here. The first is that we have to draw out the mechanism, and then the second is that we have to keep track of this carbon and see where it ends up in the product. Now the hint here in this question is crucial. This reaction involves a retro-aldol reaction followed by an aldol condensation. If they ever gave you a problem like this on an exam or something, they would have to give you this hint, because if somebody just showed me this molecule and this molecule and the fact that I was in base, I don't think I would be able to figure it out if they hadn't have given me this hint. This is very similar to one of the post-workshop questions on one of the exercises. But as we just talked about before, the first step in the retro aldol is that hydroxide the base, is going to do the conjugate addition, where it's going to come down here and attack at that carbon, move that double bond up, and make an enolate. So let's go on to the next slide here, and you can see I got those arrows that I just drew there. We have the enolate, we have the OH that's been added, and we're still keeping track of our carbon. In the next step, we're going to do that proton transfer, where that enolate is going to come down, and we're going to make this O-. So that's what those arrows would look like. We get to here. And after this, if you remember the mechanism, this is where we break apart the two molecules. In this case, however, it turns out that we had two ketones that were both on the same molecule. So this is an example of an intramolecular aldol condensation. Not any different than the intermolecular ones we were just looking at, but sometimes it can trip people up a little bit. Once we get to here, we're going to want to take apart that enolate to go back to a ketone. So now we have two ketones, and let's go back and just take a look at that radiolabeled carbon, right? The radiolabeled carbon was right here, and we formed a ketone, so it should make sense that that radiolabel is, one carbon away from that ketone. So it's right here, it's right here. That makes sense. Once we get to this part, the only thing that would make sense to get back to here would be to do the aldol condensation again, but we don't want to start from this enolate, right? If we just made the same enolate again, we would just go right back to the reactant. So we've got to make a different enolate, and if we're making a different enolate, we can see that we need to end up with a 6-membered ring. So we should probably think about making an enolate that's going to give us a 6-membered ring. And so the next enolate, there's a hydrogen there, there's a hydrogen there, there's a hydrogen there, and there's a hydrogen there, and all of them are enolizable, but the only one that's going to give us a 6-membered ring and is different than the one that we just came from would be to pull the hydrogen that's attached to the radiolabel. So going forwards, you can see that that's exactly what we do. We have another mole of base come in and pull that hydrogen that's attached to the radiolabeled carbon. We make another enolate. Now we're going forwards, right? This is probably easier to think about. This enolate is going to attack the carbonyl, just like that. We make our 6-membered ring, and again, let's just keep track of our radiolabeled carbon. When this came down to make the ketone, one carbon away, one carbon away. A question like this would probably be really smart to number your carbons if you're ever doing this on a test. Then we're going to make the enolate again, and then we can do our E1CB elimination to kick out hydroxide, and that brings us back to the product. So that is all for the aldol condensation video. I hope this was helpful, and good luck on your test.